Good evening, everyone. Welcome to Unacademy, India's largest online learning platform, which is acting like a bridge between the dreams and success story of many students like you. Good evening, Balaji. Welcome to all corners of the India, from all walks of education system. The Unacademy is serving the students in a different way. You take engineering, you can take medical field, you can take IIT, that is those who are intermediate, or for those who are in medical field, PG, whatever, whatnot. So whatever you ask, so Unacademy is with you. Thank you for joining with me on this today evening. Yeah, we'll continue our discussion. The subject which I am dealing is electronic devices. So which is common for, this will be useful for the students of ECE especially, and some part is going to be for EE students, and for some part is also useful for the instrumentation students. So the gate, and for also some, this will be useful for ESE students, engineering service examination students. This is lecture number 21, and I'm dealing with a topic called tunnel and photodiodes. Now we will discuss about tunnel and photodiodes. Today we'll discuss. Good evening, Vasu. Good evening. Good evening. So myself, Shravan Kumar, having a master's degree from JNTUH in VLSI system design. I have 10 plus years of teaching experience. So I will teach EDC subject which I am right now teaching, and again I'm teaching already unlock in app, Unacademy app, and we have digital and EMFT. Digital and EMFT. After finishing these two, we will get into this digital and EMFT subjects, right? So I have a special code called SVS10, which will be useful for the students to get 10% discount on Unacademy plus subscription. Unacademy plus subscription. So what do you mean by a plus subscription? A plus subscription is simply you'll get an access to the live classes. You have a crash courses. You have a crash courses. You have weekly tests. You have, as I told you many times, these tests are very important for any students to get success in GATE examination. And you will have some doubt solving session. Every 4th hour is going to be doubt solving session for the student. And you can have top you can have lessons in English and Hindi. The medium of communication will be English and Hindi. You have something called rank improvement batch. So those who are very strong at the basics and want to increase their rank, this will be useful for them. That is rank improvement batch. And then we have something called iconic. We have something called iconic. What is iconic is you need a you will be given a allotted a personal coach, and you will be given a study planner. Will be a best study booster sessions you are going to have, and then you will have a personalized test analysis, which is very important, sir. After every test, you'll get a section wise and question type analysis, in-depth analysis will be given for all of you, and you'll have a preparatory study material which is very much important. That is, specialized notes and practice sets will be there. Specialized notes and practice sets will be there. So those who have choose for plus subscription is having 12 months, 18 months, and 24 months subscription. So the plus subscription fee structure is going to be 27,225 rupees. It may be changed also a little bit. So, but this is going to be SVS 10, which will give you 10% discount. Which will give you 10% discount, right? So this is 34,650 rupees. But 18 months you have 34,650 rupees. Again, you'll get 10% discount based on this code SVS10. Code SVS10. For 24 months, you will have a code 39,600 rupees. So this is going to be SVS10. SVS10 is going to be the code. SVS10 is going to be the code. For iconic subscription, you'll have 12 months. For 12 months, you have a 45,225 rupees, and you're going to get SVS10 and 10% discount again. So 24 months, for 24 months it will be 67,600 rupees. So SVS 10 is a code. You can pay using EMIs, EMI facilities there, and you can use wallets, and you can have credit card. Right? All these facilities are there. All these facilities are there. So those who have not downloaded yet this Unacademy app, I would request you to just simply go and download the app. Unacademy app just consists of Unacademy learning app, and when you type in the Google Play Store, you will get this Unacademy learning app. Just download and install. After installing, step 3 is you have to select your goal. As I told you, we have a different areas. So we have NET exam, we have IIT JAM exam, we have NEET PG, and we have all other areas also. I would request you to select GATE and ESE. Good evening, Krishnaveni. Good evening. Welcome. GATE and ESE, GATE and ESE. So in this GATE and ESE, once you select, you'll have 3 types of classes. That is plus classes, free courses, and specialized courses. All these special and free courses are free. The plus classes is going to be paid. That is what I have already told you. So when you select, you can get subscription. You can get subscription. So this is a special free class series on Unacademy app. So know your basics. Know your basics. So which was started on 20th of December. So it is to target 2022 and 2023 students. 2022 and 2023 students who are preparing for GATE examinations. So what are the benefits of this? Is going to be a complete roadmap to approach each subject of every branch, and you'll be given a subject-wise strategy to crack GATE 2022-2023, and you'll be given introduction and guidance by India's top educators across all the branches. So what all the branches means? Mechanical you have, civil you have, electrical you have, ECE you have, CSE and IT, and chemical engineering. For all these branches you have this course. So use this facility. We have just now, as I told you, the video is played. Ascend 2023 for ECE and Triple students are there. So this code you can use. You can use this code. And Evolve GATE 2022. This is targeting 2022. You have something called GATE Evolve. So these are the top educators of Unacademy, and you can use these codes. WE GATE 10 and the ECE GATE 10. If you are ECE students, you can use this. This is also both of them are started on 21st of December. These courses are started on 21st of December. The medium of instruction will be in English and Hindi. English and Hindi. And you all can follow me on Unacademy. On this. Okay. Yeah. Now we will discuss the problems on Diode. Before discussing so as usual, what we'll do is generally we'll do our discussion. So in the last class, what we have discussed. So we have discussed about breakdown mechanisms. We have discussed about breakdown mechanism in the diode. We have 2 types of breakdown mechanisms. They are avalanche breakdown, Zener breakdown. So this is what avalanche breakdown, Zener breakdown. As I told you, avalanche means there is a sudden increase of the snow. So there will be sudden increase of the charge carriers in this breakdown. Sudden increase of the charge carriers in this breakdown due to the temperature difference, right? Majorly the temperature difference. And the Zener breakdown is something different. I will discuss that later. So avalanche breakdown happens in only lightly doped diodes. Avalanche breakdown happens in only lightly doped diodes, and it is because of the collisions, or when the charge carriers are collide with electron holes present in the covalent bond. Electrons present in the covalent bond, these covalent bonds will break and new charge carriers will come. And this secondary particle also accelerates. Again, the collisions will happen to generate new electrons and holes. So now this process is a cumulative process. Continuously it increases, and avalanche multiplication is that what called, right? I think I have explained you this. This is cumulative. Cumulative process. It increases in multiplication. It increases and increases and increases. It will reach to some voltage. So this is the what M value. M is a multiplication factor. M is a multiplication factor. M is going to be M multiplication factor. M is equal to 1 by 1 minus VR by VD whole power n. 1 minus So where M is a carry multiplication and n is a constant for it is going to be 4 and p type for n is going to be 2. The VR is applied reverse voltage which is required. VT is a breakdown voltage which we have discussed. So due to this avalanche effect, the junction is said to be breakdown and the current starts increasing rapidly is what we discussed. But important point is the avalanche breakdown occurs only when the breakdown voltage is more than 6 volts. More than 6 volts. This you need to remember. This you need to remember. And here comes Zener breakdown. The Zener breakdown is because of the very intense electric field, which is present inside, which will generate the large number of electrons. And that effect is called Zener effect. That effect is called Zener effect. So Zener breakdown mechanism is called Zener breakdown, and the Zener breakdown happens for the voltages which is having breakdown voltage which is less than 5 volts. The temperature depends on breakdown voltage we have discussed. So as the temperature increases, avalanche breakdown increases. As temperature decreases, avalanche breakdown decreases. So Zener breakdown decreases. So we have discussed avalanche breakdown as a positive temperature coefficient, and Zener breakdown has a negative temperature. So Zener breakdown has a negative temperature coefficient, and avalanche breakdown has a positive temperature coefficient. This is what we discussed in detail. What is then Zener diode we have discussed? Zener diode is nothing but a heavily doped diode, which is very important. It's a very heavily doped diode, and the operation of a Zener in the normal PN junction diode, the forward bias characteristics of a PN junction diode as well as Zener diode will be same, right? But the reverse saturation current there will be sudden increase of reverse saturation current, and when that happens is nothing but reverse breakdown voltage. That happens for reverse breakdown voltage. And we have seen the symbol of the Zener diode. As I told you, the symbol of the Zener diode contains Z. The symbol of the Zener diode contains Z, right? So when the reverse voltage exceeds the reverse breakdown voltage, the current through it changes drastically, right? But the voltage across it remains almost constant, And this is what I told you. So Zener diode must be operated in between. Now, for a small change in the Zener voltage, that is breakdown region voltage, there will be high change in the current. It means if you think inversely, for high change in the current, also your breakdown voltage is not changing. And this RZ is the reverse dynamic resistance of the Zener diode, which is equal to the 1 by slope of the reverse characteristics of Zener region, that is delta Vz by delta Iz. So, and the dynamic resistance will be very small, and it is of the order of few tens of ohms. And this is the difference. I think yesterday Balaji was asked me to do some differences. These are the major differences. These four are the major differences of a Zener and avalanche breakdown mechanisms. This is the equivalent circuit of a Zener diode. So as I told you, Zener when it is a breakdown, when the Zener diode is a breakdown, it acts as a positive voltage drop. You can see here. Plus Vz is going to be there. Plus Vz, it acts as a voltage source of Vz. And applications we have seen voltage regulator. So we have seen what is the voltage regulator. Voltage regulator will give constant output voltage irrespective of the change in voltage and change in load. Irrespective of change in voltage and change in load variations. Mahendra, good evening. Good evening, Mahendra. Good evening. Welcome. And the factors which are determining stability is, now we have seen this output voltage depends on the input voltage, load current, and temperature. So this is what we have discussed. And these are the factors. SV, what is SV, sir? SV is the factor which is because of the input voltage. That change in output by change in input. Change in output by change in input by assuming the remaining two as a constant. That is load resistance constant, temperature constant. Right? So what is R naught? R naught is going to be change in voltage by change in current by assuming change in input and change in temperature as zeros. Right? Output resistance. So temperature coefficient. Temperature coefficient. So it means change in output voltage with respect to temperature having change in input voltage 0 and change in input current 0. See, whenever there are the three variables, this is input, V input is variable, IL is variable, T is variable. Because of that, while we are calculating, we assume remaining two are constant, and only this is changing. It is like superposition theorem. It is just like superposition theorem which you apply in networks. Yes or no? You apply superposition theorem when we have more than 2 or 3 sources. So this is same as that. This is same as that. And we have seen what is load regulation. Load regulation is what? V no load minus V full load by V no load. So this V no load means V no load current. Voltage at no load current. Voltage at no load current. No load current. No load current. The V full load current. V full load current. So you should remember this. You should remember this. Okay. Okay. Zero load current. V no load means zero load current. Zero load current. No load current. Don't think that this. So you have to remember this point. You have to remember this point very importantly. You have to remember this point very importantly. And now we have seen the Zener diode as a voltage regulator. So what is meant by voltage regulator, sir? As I told you, for the Zener diode should give you. Now we will discuss in detail, sir. Now we will discuss in detail. I'll just focus on this now for a few seconds, few minutes. I'll focus on this. Karunakar, good evening. Karunakar, good evening, Karunakar. Welcome. Yeah, this Zener diode as a voltage regulator is very important. This Zener diode as a voltage regulator means what, sir? For change in input voltage and change in load current and change in load and change in temperature, this should give you constant output voltage Vz. Zener voltage. It should give you Zener voltage. It should give you Zener voltage. So for that we have seen. So somebody asked why it is not possible to connect. I think Krishnaveni was asked. Krishnaveni asked, sir, what is the why we are not using Zener diode in series? In series. So there is no use of series. I think some students also answered this question in the last class. I think Mahindra answered this question. I think. Okay. So for V input greater than or equal to Vz, that Zener diode acts as a on. So it means breakdown happens. Breakdown happens. When the breakdown is happening, V output is going to be Vz. For V input less than Vz, for V input less than Vz, this is going to act as a open circuit, and your output is going to be again depend on. You should apply KVL and you should find out what is the output voltage. What is the output voltage? Now we have seen for both VI and RL are fixed. For both V in and RL are fixed. When V in RL are fixed, what you get is Z is going to off. For V input less than 0, you get Z is going to off. We will do some problems based on this concept so that you all understand very clearly. So that you all understand very clearly what is what. So for fixed value of VI and variable RL. So when RL is changing, it means when the RL value is increasing, the current flowing through this should be decreased. Yes or no? As RL value is increasing, IL should decrease. When IL is decreasing, IZ decreases. IZ decreases. Why, sir? Why, sir? Because both voltage drop across these two must be same. Voltage drop across these two must be same. Are you getting my point? Are you getting my point? Remember, this IL and RZ, the multiplication of IL and RZ should be same, constant. So when RL is increasing suddenly, definitely IL should be decreased. So when the IL is decreased, are you getting what I mean? So don't get confused what I'm saying here. As the RL value is increasing, see, we have concluded that this voltage is constant Vz. If this Vz is constant, obviously the voltage drop across this RL should be Vz only. We know that the formula V is equal to I into R. I into R. Now this is constant. This is constant. Let's say this is going to be Vz equal to Vz. This is constant voltage Vz. When this is Vz, if IRL is increasing, obviously IL should decrease. But when IL is decreasing, what we know, sir, I is equal to, from this total current, I is equal to IZ plus IL. IZ plus IL. The decreased load current value will be compensated by the current passing through the Zener diode. See how great this Zener diode is. How great this Zener diode is. Somebody is losing the value, but it is helping. Right? So we should appreciate this Zener diode. We should appreciate this Zener diode. So it is not creating problems. It is not creating problems. It is trying to solve the problems. It is trying to solve the problems. So as IL value is changing, decreasing, so IZ increases. IZ increases. IZ increases. So then what is the I value? I value simply here we know. So let's say some voltage will be Vz here. So obviously it's going to be Vi minus Vz by R. It's going to be Vi minus Vz by R. So you need not worry about this. So I is going to be Vi minus Vz by R. So now here comes the story. So as you decrease and decrease the value, as you increase the value of load resistance RL increases. So at some point of time, this RL becomes maximum. When RL is maximum, obviously IL should be minimum. Obviously, IL should be minimum. So when this IL is minimum, the current flowing through the Zener diode will be maximum. Yes or no? So then IL is minimum, this IZ should be maximum. When IL is minimum, this IZ should be maximum. If you consider in the opposite direction also same. Let's say if your RL is very small, if this RL is very small, decrease and decrease and decrease, then this IL becomes maximum and IZ becomes minimum. That is what I think we have discussed in the last. Yes. So RL minimum is going to be what? V naught by IL maximum. So how to calculate IL maximum? You have some formula. Same formulas are actually you have only I plus IZ. See IL maximum as just now I told you, right? Here, if this is maximum, if this IL becomes maximum, this IZ should become minimum. This IL becomes maximum, this IZ should become minimum. Okay, this is the theory is very important. This theory is very important. I'm trying just now because of that reason I'm trying to explain it here again. So I will calculate the value of RL minimum, IL maximum. All these things are same. So Vi minus Vz by R, Vi minus Vz by R is nothing but current flowing. So IL maximum is going to be Vi Vz by R. So what is the RL minimum? Whenever IL maximum happens, RL minimum will happen. So these two are interrelated. So IL maximum is equal to Vi minus Vz by R means what? Is it not same as that value of I? Because you are neglecting the IZ, that is IZ is becoming 0. Current flowing through this becomes 0. Then only this IL maximum becomes I, because I is the source. So IL maximum is going to be Vi minus Vz by R. Vi minus Vz by R. Right? So now what happens, sir? You have a fixed resistance. Case 3, you have fixed resistance and a variable input. Now you are trying to change the variable input. So when your input is varying, obviously the current flowing through this load resistance changes. So when the current flowing through this is changing, so the IZ value is changing. Why? Because as I told you, this RL is constant. When this RL is constant, obviously the IL should become constant because this Vz is the same voltage across this RL. So the voltage across this load resistance is not changing. When the voltage across this load resistance is not changing means its current flowing through that load resistance is also not changing. Because the voltage drop across this should be constant. Then what happens for the increase or decrease of the input voltage? Because of this, definitely the current changes here. Whenever the current is changing here, the increased or decreased current will be made by the load, the Zener diode IZ. So whenever IM is maximum, it's going to be VR maximum plus Vz. Why, sir? This VR is constant. Sorry, this VZ is constant. The voltage drop across Zener diode is constant. Are you able to understand or not? Are you able to understand or not? Please respond. Please respond, sir. Please respond. Quickly. Balaji responded. Balaji responded and others did not respond yet. I think others are sleeping. Vasu, Krishnaveni. V input is parallel to VZ. Who told, sir? Who told V input is parallel to VZ? It is not parallel to VZ. In between you have a resistance. Vasu, parallel means you should not have anything in between. Anything in between. This is what parallel. This is what parallel. But this is not, let's say it's going to be R1 and R2. R1 and R2. Let's say in between you have some other resistance. Do we call this R1 and R2 in parallel? R1 and R2 in parallel? No, these two are not parallel. So obviously this voltage, obviously this and these two are in parallel, man. So these two VZ, that Zener diode and load resistance are in parallel. Okay, Krishnaveni, okay, very good. So this load resistance RL and Zener diode are in parallel, but V input and VZ are not parallel. Zener diode and V input are not in parallel. They are not in parallel. In between you have some resistor R, sir. You can't neglect this resistor R. You can't neglect this R. Okay. So they are not in parallel. So for V input maximum, VR should be maximum. That is V input maximum is equal to IR maximum to R. So for V input minimum, VR minimum plus VZ. For VR minimum plus VZ. Now I think this is what we have discussed. I think till now all the theories same. Hope you are happy with the theory what I have discussed. If you have doubts, please ask me. Now we will start some problems. So before starting the problems, let me know either is all the theories clear or not on the Zener diode. On the Zener diode, if the theory is clear, we can easily understand the problems and we can solve the problems very easily. If you are okay, we'll start discussing the problems. If you are okay, we'll start discussing the problems. And most of the problems now, what we are discussing is all previous gate exam problems only. I don't remember the year in which they have come. In which year they have come. In which year they have come. All these are the problems only. All these are problems only. Okay. Shall we start discussing problem number 1? First problem. First problem. We'll start discussing problem number 1. First problem. Okay. Now, in the circuit shown below, the Zener diode is ideal Zener diode with Zener voltage of 6 volts. That is saying Vz is going to be 6 volts. Vz is going to be 6 volts. The output voltage V0, in volts is. So he's asking what is the output voltage? 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 Now, first of all, output voltage 6 volts. Okay, we will see. Krishnavedi, we will see whether you are right or wrong. Whether you are right or wrong. We'll try to analyze the circuit. We'll try to analyze the circuit and we'll come to a conclusion. Now to calculate whether the Zener diode is on or off, let's calculate what would be the voltage drop across the Zener diode. What would be the voltage drop across Zener diode by calculating this voltage across this V0, right? So what would be the voltage drop across this V0, sir? So apply voltage division rule. Simply we'll apply voltage division rule. So V voltage drop across V0 diode is going to be applied voltage V into the resistance, the left resistance 1 kilo ohm by 1 kilo ohm plus 1 kilo ohm resistance. So the voltage drop across this Zener diode, this is voltage drop across Zener diode right now. Voltage drop across Zener diode is going to be 10 volts into 1 kilo ohm by 1k plus 1k. That is, now how much it's going to be, sir? I'll write simply 10 by 2. Kilo ohms will get cancelled. Kilo ohms and kilo ohms get cancelled. So V across the Zener diode is going to be 5 volts. 5 volts. 5 volts. Whenever, Balaji, good. Sir, what is the breakdown? What is Zener voltage, sir? Vz. Vz. So the voltage which the voltage you are applying here, the Krishnavedi, what you might have thought is this 10 volts voltage is across the Zener diode. This is what you thought, right? But you should consider the voltage across the Zener by considering the voltage drop across this 1 kilo ohm also. This 1 kilo ohm also. Yes, 1 kilo ohm also. Now, as a Zener diode voltage, right? So this V is less than Vz. So Zener is not breakdown. Zener is not in breakdown. So Zener is off here. So this, because this 5 volts is less than 6 volts, which makes Zener diode off. Zener diode off. It means now how the circuit looks like, sir. So this Zener diode is open circuited. This Zener diode is open circuited. This Zener diode is open circuited. Whenever the Zener diode is open circuited, now what happens, sir? This is this 10 volts you have here, 10 volts here applied. So this is going to be 1 kilo ohm. This is going to be 1 kilo ohm. The voltage will be equally distributed. So here you will have 5 volts means here you definitely will have 5 volts. So what is the output voltage? What is the output voltage? Output voltage V0 is going to be 5 volts. Output voltage V0 is going to be 5 volts. Okay. Correct, Balaji. What you are told is correct. What you are told is correct. What you are told is correct. Okay. Okay. So the output voltage. So answer is 5 volts. Answer is 5 volts. Answer is 5 volts. Okay. Now we'll move to the next problem. A 6 volts Zener diode shown below has a 0 Zener resistance and knee current of 5 milliamps. Okay. The minimum value of R, value of R so that the voltage across it doesn't fall below the 6 volts. Voltage across the Zener diode voltage. So what is saying, sir? The voltage drop across this resistance should not fall below 6 volts. Should not fall below 6 volts. So what is the given condition, sir? He says the Zener resistance RZ is going to be 0. VZ is going to be how much? 6 volts. And he is saying knee current, knee current is going to be 5 milliamps. Knee current I is going to be knee current. So what do you mean by knee current, sir? Knee current is nothing but IZ minimum. IZ minimum is going to be 5 millivolts, 5 milliamps. So sir, so don't see what is it. I'll explain you again here. You may get a doubt, sir. Why did I consider knee current and IZ minimum? I'll show you here. Need not worry. Don't get confused now. I'll draw here. So the property. Now after this point, there is a sudden increase of the current. Yes or no? There is a sudden increase of the current. There is a sudden increase of the current. There is a sudden increase of the current. So now this current is called knee current. Yes or no? This current is called knee current. Knee current. Why, sir? It simply looks like knee or not? Your knee, your leg knee. Is it not looking like a knee, sir? Knee current. Your leg knee you have, yes or no? Leg knee. This is called knee current. So I can say this knee current is nothing but the minimum value of the IZ minimum, I can say. I don't know what is IZ maximum. I don't know IZ maximum, but indirectly has given IZ minimum is equal to 5 milliamps. 5 milliamps. So remember, indirectly has given IZ minimum is equal to be 5 milliamps. 5 milliamps. Okay. Now we have to calculate the total current. Now we have to calculate the total current. So how will you calculate the total current? How will you calculate total current, sir? Assume that 6 volts is saying, obviously it should be in 6 volts means I'll draw. So what is saying, sir? This resistor, this Zener, and this is some input voltage. How much input voltage? I didn't see. 10 volts, I think. This is 10 volts. This is 50 ohms. And then this is some resistance R. Some resistance R. Sir, whenever this Zener, whenever the voltage drop across this R should not fall below 6 volts means this Zener voltage is there. So here you have 6 volts. And here you have 10 volts. And the current flowing through this is I. So how will we calculate the current? Wait, I'll tell you, Balaji. You're almost there, but not exact value. You're almost there, but not exact value. R is not exact value what you have calculated. I'll just wait for another 2 seconds. IL you got Krishnaveni. But what is I milliamp? Acha, total current I. So total current I is going to be correct. But what is asking? Is asking the value of R. Krishnaveni, you are doing good. You're doing good. But is asking the value of R. You have to calculate the value of R. The currents are correct. Whatever currents you have calculated current, those current, correct. So IL is going to be this 10 volts minus 6 volts by 50. 10 volts, 10 volts minus 6 volts by 50. So how much will get? I is going to be, will get 80 milliamps. Will get 80 milliamps. Okay, you get 80 milliamps. Correct, correct. So once you get 80 milliamps, now how will you calculate, sir? You can calculate what would be the maximum load current. So what would be the maximum load current? What is saying, sir? The minimum value of R is asking for R minimum. So when he is asking for R minimum means its corresponding current will be IL must be maximum. IL must be maximum. When IL is maximum means the total current I is going to be what you will get, sir? IZ minimum plus IL maximum. Yes or no? So from this we need to calculate IL maximum. So IL maximum is going to be I minus IZ minimum. Vasu, are you able to understand or not? Because I didn't see any response from you. Vasu, are you there? Okay, IL maximum is going to be 80 milliamps minus how much this IZ minimum? IZ minimum is going to be 5 milliamps and this is going to be 80 milliamps. So IL, okay. IL maximum is going to be simply 75 milliamps. 75 milliamps. Now you can calculate R minimum. So now you can simply calculate R minimum. So R minimum is going to be how much? R minimum is going to be how much, sir? Simply you can calculate V0 voltage by IL maximum. So how much is R max voltage? He's saying always it should maintain 6 volts. In the given problem, what is saying, sir? It should not fall below. Does not fall below 6 volts. Means V0 must be equal to 6 volts by IL maximum. How much is IL maximum we got? 75 milliamps. 75 milliamps. Now tell me what is R minimum from this? Okay, correct. Now what you got is correct. 80 ohms. 80 ohms. 80 ohms is the right answer. 80 ohms is the right answer. Correct. RM minimum is equal to 80 ohms. 80 ohms. Okay, shall we move to the next problem? Yeah. So here comes the problem. A Zener diode is shown in the below figure has a knee voltage of 5 milliamps and a maximum allowed power dissipation of 300 milliwatts. What are the minimum and maximum load currents that can be drawn safely from the circuit, keeping the output voltage constant 6 volts? 6 volts. Can you try? Can you try for 2 minutes? I'll explain otherwise. Can you try, sir? Almost same. This is almost same, but he's asking us to calculate. Load current, IL maximum, and then IL minimum is asking. So he's asking for these two values. And what is the given data? Given data says knee current. Knee current means IZ minimum. IZ minimum is 5 milliamps. It is also given PZ. PZ is going to be maximum allowed power dissipation is saying 300 milliwatts. It means indirectly he has given what is PZ? PZ is going to be how much, sir? We know PZ is going to be IZ maximum into VZ. So from this you can calculate IZ maximum. So you can calculate IZ minimum. Already IZ minimum is existing. We can calculate IZ maximum from this PZ. Okay, IZ maximum you can calculate from PZ. Now then you can calculate what would be. Now then calculate the value of I. How will you calculate the value of I? Simply, this is the voltage and this is the voltage. How much is the voltage here? This is 6 volts. This is 9 volts. So 9 volts minus 6 volts or 50 volts, you will get I value. So if you get I value, IZ minimum, IZ maximum, it is very easy for you to calculate IL minimum, IL minimum, IL maximum. Okay. So I'll do that now. I'll do that now. So this is also all our previous gate problems only. All our previous gate problems only. Don't think that I'm teaching something different. All our previous gate problems only. So IZ minimum we know. IZ minimum is going to be 5 milliamps. So what is IZ maximum? So PZ is going to be IZ maximum into VZ. So from this IZ maximum is going to be PZ by VZ. So what is saying, sir? It's going to be PZ maximum is going to be 300 milliwatts by VZ is 6 volts. 6 volts. So from this, so IZ maximum is simply, what is, sir? 6 5s are 300. So 50 milliamps. 50 milliamps is IZ maximum. Correct. IZ maximum is going to be 50 milliamps. Both of you are correct. Balaji and Krishnaveni, both of you are correct. Right? So now we need to calculate the value of I. I is nothing but simply 9 volts minus 6 volts by 50. How much you'll get? How much you'll get? You'll get 3 by 50. I can say 60 milliamps. 60 milliamps. You'll get I is equal to 60 milliamps. I is equal to 60 milliamps. Then what is I, sir? I is equal to IZ minimum plus IL maximum, or I is equal to IZ maximum plus IL minimum. So if you want to calculate IL minimum is going to be I minus IZ maximum. I minus IZ. How much is I? I got 60. What is IZ maximum? You got 50 milliamps. So total IL minimum is going to be 10 milliamps. So if you want to calculate IL maximum, the formula is going to be I minus IZ minimum. So it's going to be 60 minus IZ minimum is 5. So you'll get 55 milliamps. 55 milliamps is going to be IL maximum. IL maximum. So this is going to be one answer. This is going to be another answer. See what he is asking. He is asking for order of minimum and maximum. Minimum and maximum. Order is also very important. Order is also very important. IL minimum is 10 milliamps. IL maximum is 50. Correct. Correct, Krishnaveni. Correct. Correct. Good going. So minimum is 10 milliamps, maximum is 55 milliamps. Minimum is 10 milliamps and maximum is going to be 55 milliamps. Now, this is the super problem. This is a super problem. I think this is asked in 2016, I think. 2016, as per my knowledge. This is from 2016 question paper. Think and tell me what is this. Can you guess what is the answer for this? What is the answer for this? This is 2016 gate problem. 2016 gate problem. First, read the problem carefully. The IP characteristics of The Zener diodes D1 and D2 are shown in the below figure. Very happy. Figure 1. These diodes are used in the circuit given in figure 2. Very happy. If the supply voltage is varied from 0 to 100 volts, breakdown occurs in. Sir, answer is either it is going to be 50 milliamps because he asked that maximum power. So that either maximum, hey, you are just confused, Balaji. You are just confused. You are just confused. See, if IZ is equal to 50 milliamps, IZ is going to 50 milliamps. So now, see, it is no way connected to this. This is no way. This PZ is maximum is no way connected to this. Right? This load, IL current, no way connected to IL current. Right? IZ maximum is how much? You have already calculated IZ maximum. What is IZ maximum? When IZ maximum is this, so IL minimum is how much? IL minimum is 10 milliamps. Yes, for IZ maximum, IL minimum is 10 volts, 10 milliamps only. Don't get confused. Don't get confused. Balaji, don't get confused. Don't get confused. This 55 milliamps is IL maximum. When IL is maximum, IZ is minimum. IZ is minimum. Why are you confusing? Why are you confusing? There is no way related. This IL minimum and IL maximum is no way related to PZ. That is headache of PZ. Okay, come back to this problem. Come back to this problem. So whatever is saying, sir, this is the IV characteristics of these two diodes D1 and D2. This Zener diodes. Both of them are Zener diodes. Right? So and they are in series. Both diodes are parallel. No, the diodes are in series, appa. Vasu, the diodes are in series, na? They are not in parallel. Diodes are in series, not they are in parallel. The diodes are in series. Why are you thinking that they are in parallel? So what is saying, sir, that diodes D1 and D2 are connected like this, and this input is voltage changed from 0 to 100 volts, 0 to 100 volts, right? These diodes are the breakdown occurs in which diodes? In which diodes the breakdown occurs? You can see here the option 1 is, as you are unable to see, I am just leaning down. So option 1 is D1. Option 1 is D1 only, or otherwise I'll write option 1 here. Option A, D1 only. Option B, D2 only. Option C, both D1 and D2, and option D, none of D1 and D2. None of D1 and D2. Very interesting problem is this. Very interesting problem is this. Sir, now you can see here, you can see some currents here. This is the reverse saturation current of, I01 of this diode D1, constant current. This current is going to be I02, the reverse saturation current. The reverse saturation current of. So which current is higher, sir? Which current is higher here? Which current is higher? I02 or I01? I02 or I01? This is low value, right? I01 is low value, I02 is high value, right? So now you can see here for this value, if you choose a current in between these two, if you choose a current in between these two, so when I am increasing slowly from 0 to 100 volts means the current slowly increases. The current slowly increases. The current slowly increases. When the current is slowly increasing means, so I0, let's say I01 is 1 milliamp or 1 microamp, and this I02 is going to be 2 microamps. I02 is going to be 2 microamps. I02 is 2 microamps. So when you are slowly increasing this voltage from 0 to 100 volts, now slowly what happens, sir? You can see here, by this time, let's say you are at 1.5 microamps. Understand what I'm saying is, assume that I01 is going to be 1 milliamp, and then I02 is going to be 2 milliamps. So as input is varied from 0 to 100 volts. So in between, let at I0 is equal to 1.5, we will analyze this. When I0 is going to be 1 milliamp, when Y0 is going to be 1 milliamp, now by this time, what happens, sir? This diode has already broke down. What is this diode? This diode is D1 diode. Sir, understand it very carefully. Understand this very carefully. See, before this diode D2 breaks down, the diode D1 has already break down. The diode D1 is already breakdown. Then what is the breakdown voltage of diode D1? So now what happens, sir? The diode D1 is breakdown. When the diode D1 is breakdown, what is its corresponding voltage? VZ is saying it is going to be 80 volts. It is 80 volts. So if it is diode voltage is 80 volts, so who will share the remaining, sir? How much is remaining? 20 volts. So this diode D2 voltage drop across this diode D2 is going to be 20 volts only. 20 volts only. To make this diode D2 breakdown, we need how much voltage, sir? 70 volts is required. Remember always, it's just like a pipeline. Always remember, when the diodes are in series, it's simply like pipes. Let's say a small pipe is connected here, and then a big pipe is connected here. Whatever output is coming is because of this current only. So whatever current is coming here, the same current will come. Though this capacity is very high, this current capacity is high, but what happens, sir? This small current only will come out. This small current will only come out. No, Balaji, just don't be in hurry. Understand now. So now what happens, sir? When you are slowly increasing from 0 to 100 volts, so when the input crosses 80 volts, this diode D1 breaks down. The breakdown for diode D1 occurs already. So once the diode D1 breaks down, now still this current is flowing here, but the diode D2 is not in breakdown. Diode D2 is reverse bias. but the breakdown is already occurring for diode D1. So to make diode D2 breakdown, we need this 20 volts is there here because 80 volts is occupied by this fellow, and you will have 20 volts here. So how much voltage extra is required? If you apply another 50 volts, then diode D2 will also break down. So now, if see for that means in 80, so if you apply 130 volts, is that 130 or 150? 150 volts, sorry. So if you apply another 150, total 150 volts, then the diode D1 and D2 will break down. But here only diode D1 will break down. So the then breakdown occurs only in the diode D1. So the option A is the right answer. Option A is the right answer. This is theory, sir. This is a super question. This is seriously a super question which is asked in 2016. Many students will get confused. Many students will get confused. Many students will get confused. Okay. Hope you got the point. Hope you got the point. Hope you got the point. Yes or no? Did you understand? So this understanding of this problem is very important. That's the reason I am taking a lot of time to explain this problem. Theory, pure theory. Yeah, yes, you are correct. Yes, you are correct, Vasu. So if that is the case, both of them are see. If a current is flowing, if a small current is flowing, this means the same current will flow to this also. Reverse saturation current is existing. Reverse saturation current is existing in this D2 also. You are talking about ideal case. You are talking about ideal case, Balaji. You are talking about ideal case. But when he's clearly saying there is a reverse saturation current, there is a reverse saturation current. In that ideal case, this is open circuited. In the ideal cases, both of them are open circuited. But if this is breakdown means this current is also flowing. Remember, same current, that I01 current is flowing through both diode D1 and D2. You are talking about ideal case. In series, current is gone. Yes, same current. Yes. To answer your question also, Vasu, both current flowing through D1 and D2 are the same. That's what I told. That's what I explained here. That's what I explained here. The current which is flowing to the small diode is same as the current flowing to the large diode. Balaji, you're talking about ideal case, but practically what's happening here is a small reverse breakdown voltage, reverse current is flowing through this. Reverse current is flowing through this. So the same current is flowing through this. It is very clearly mentioned here. They are not ideal case. If that is the ideal case, zero current. You have mentioned zero current. You have mentioned zero current. Yes. Hope it is clear for Vasu also. Vasu, it is also clear for you. Vasu, it is clear for you, I think. If you guys are okay, we'll go to the next problem. Okay, very good. This is 2016 model question. The answer is going to be D1. Answer is going to be D1. Sorry, A. Sorry, D1 only. A. Option A. Now, in the circuit shown below, the knee current of the ideal Zener diode is going to be 10 milliamps. To maintain 5 volts across the load resistance RL, the minimum value of RL in ohms and the minimum power rating of the Zener diode in milliwatts respectively are. Respectively are. Sir, this problem is very simple. Don't think that this is some different circuit. Don't think that this is some different circuit. So the circuit is as same as the same circuit, sir. to make you confused, he made like this. To make you confused, he made like this. Circuit is no different circuit, sir. The circuit is same as that of the previous circuit only. Same as that of the previous circuit only. Just to make you confused, so he changed that. This and this are same. This and this circuits are same, equal. They are same, equal. 10 volts, 100 ohms, 5 volts DC, 5 volts Zener, the RL. Don't think that the circuit is something different. Don't think that the circuit is something different. The circuit is as same as the previous case. As same as the previous case. Can you do that? He's asking RL minimum. He's asking RL minimum. First find out what is the current flowing through 100 kilo ohms, 100 ohms resistance. How will you find it under current, total current? First simply find the current I. Simply find the current I. Simply find the current I. Then IL minimum is given. IZ minimum is given. IZ minimum is already IZ minimum is given. 150 ohms. 150 ohms. 150 ohms. No. You see once again. First let me know what is IL. To get RL minimum, you should get RL maximum. So what is RL maximum? First you tell me. This is 5 volts here. Then 5 volts, 10 volts here. So this low the current across this is how much? I. I is going to simply I is going to be 10 minus 5 by 100. So I is going to be how much? 5 by 100. So can I write this as a 50 milliamps? Total current I is going to be 50 milliamps. He mentioned I knee. I knee is nothing but IZ minimum. IZ minimum. So what is IZ minimum? IZ minimum, how much he mentioned? 5 amps, 10 amps, 10 milliamps. So 10 milliamps. So 10 milliamps. 10 milliamps. So for 10 milliamps means that now IL maximum is going to be how much? 50 minus 10. So it's going to be 40 milliamps. So 40 milliamps. 40 milliamps. So what is the maximum RL value? So RL minimum. So RL minimum is nothing but V output by IL maximum. So it is 5 volts by 40 milliamps. So what is RL minimum then? Now tell me. Balaji, now tell me the answer. RL minimum. Correct. Correct, Krishnavani. Now you got the right answer. It is going to be 125 ohms. 125 ohms. It is going to be 125 ohms. You are right. You are right, Krishnavani. You are right. Similarly, find out what is He's asking for what? Balaji, what is asking? He's asking minimum power rating of the Zener diode in milliwatts. Minimum power. Minimum power. Minimum power rating. Minimum power rating of the Zener diode. So PZ minimum is going to be IZ minimum into VZ. How much is VZ? 5 volts. So what is IZ minimum? IZ minimum, correct. IZ minimum is 10. So it's going to be 50 milliwatts. 50 milliwatts. Okay, next problem. This is the problem. Sir, can you please take this problem as a homework? Please take this problem as a homework, because now we should discuss about next problem, please. This is going to be 200. This is 200. 200 ohms. 200 ohms. Balaji, in enter wrongly as okay. Okay, Balaji. Okay. Okay. No problem. Please do it as a homework so that we'll move on to the next topic. So that we'll do. So consider this as a homework and note on the answers. Tell me the answers. Tell me the answer. Do you want me to tell the answer today or tomorrow? Do you want me to tell the answer today or tomorrow? You will do it, right? You will do it, right? You'll do and tell me the answer tomorrow. Tell me the answer tomorrow. Okay? Okay, tomorrow we'll see the answer. So we'll go to the next topic. So we have something called tunnel diode. Very interesting topic. Very interesting topic, this tunnel diode. Forget about everything, sir. Just think about the word tunnel. Just think about a word tunnel. Just think about a word tunnel. So what do you mean by tunnel, sir? Tunnel is something. So tunnel is something. See, let's say you have a very, very big rock, right? So if you want to go from this side to this side, either you have two ways. You have two ways. Way one, you'll just go from this side like this and you'll go and meet here, right? Or what you will do, sir, you will tunnel this rock. You will tunnel this rock and go straight. Okay, you have two ways of going. Let's say this is a very, very big rock or hill. Let's say you have a hill. You have this a big, very big hill. You have two ways to go from point A to point B. From point A to point B, you have two ways. One thing is you can go around. You can go around the hill and reach this destination B. Or you can go by making a tunnel. By making a tunnel from A to B, and you can reach very easily. You can reach very easily. Sir, there is one person in Bihar. There is one person in Bihar. His name is Dashrath Manji. I should mention his name here. His name is Dashrath Manji. Are you able to see here? I'll write here. Dasharath Manji. You know why I am trying to mention his name here? Why I am trying to mention his name here is this is the person, Dasharath Manji. What he did is alone, with single-handedly, by working for 20 years, 20 years, he made a tunnel to go from his village, to go from his village to a hospital. A hospital. This is the village which doesn't have road facility. So his wife died because of no road transportation. No road transportation. So by taking that as an pain and to make the other village people to make comfortable, what he did is he was sleeping, doing everything on the hill itself, and he made a tunnel. He made a tunnel, and that great man is Dasharath Manji. Dasharath Manji. If you have a time, just go and search his name in the Google, and you see he has become one day CM. He was also one day CM for 1 hour CM, actually 1 hour CM for Bihar. 1 hour CM for Bihar. He was 1 hour CM for Bihar. Such a great person he is. Such a great person he is that he made a tunnel. Let's come back to our discussion. Why we are discussing all these things here is so far in all the diodes what we have discussed is we know that there is a potential barrier. There is a potential barrier. As the reverse voltage or the positive voltage which you are applying, as the voltage you are applying, now what happens, sir? The height of the potential barrier start decreasing and decreasing and decreasing. At some point of time, this potential barrier is decreased, disappeared, disappeared. Now what happened? The normal PN junction case, the normal PN junction, the normal PN junction, a normal PN junction, what we have seen here is definitely we have a potential barrier. Definitely we have a potential barrier minus plus minus plus minus plus minus plus. We have a potential barrier. As we apply positive voltage, as we apply a positive voltage, now what happens, sir? As you apply positive voltage, this potential barrier start decreasing, decreasing, and decreasing. Suddenly this disappears after, let's say, some voltage of 0.7 volts. So now after disappearing, the charge carriers, holes will move from this area to this area, and electrons will move from this area to this area. This area to this area. But in some cases called a tunnel diode cases, now what happens, sir? This this junction, they will try to create a hole. They will tunnel them. The charge carriers will tunnel the potential barrier and go from one area to other area. They will not wait till the potential barrier size becomes zero. The potential barrier size becomes zero. No, what happens is here, these charge carriers will try to create a hole. And so that they'll enter from other side. So that process is called tunneling. That process is called tunneling. That process is called tunneling. Okay, that is the reason why they are given a name called tunnel. They are given a tunnel diode. Tunnel diode. The conduction process here is different. The conduction process here is different. The conduction process here is different, not same as the previous one. So what is the difference between that diode and this diode? Now we will see here very importantly. A normal PN junction has an impurity concentration of 1 part per 10 to the power of 8. It means for 10 to the power of 8 atoms, only one impurity is added. Understand what I am saying? For 10 to the power of 8 atoms, only one impurity atom is added in a normal PN junction diode. in a normal PN junction diode. Now because of this, what happens, sir? You will get 5 into 10 to the power of minus 4 centimeters. That is 5 microns of potential barrier is coming. For a normal PN junction diode with a normal impurity concentration, you will get 5 microns as a potential barrier size. Right? Now, if the concentration of the impurity atoms is greatly increased, that is 1 part in 10 to the power of 3, for every 1000 atoms, 1 impurity atom is given. That device characteristics are completely changed. So you may ask, sir, Zener diode is also heavily doped. Yes, the Zener diode range is 10 to the power of 5. The Zener diode range of atoms is 1 in 10 to the power of 5. But here what I am trying to do is 1 in 10 to the power of 3. This is very high value. Very high concentration. Very high concentration is existing. Right? So understand the difference. For PN junction, it is going to be 1 part in 10 to the power of 8. For Zener, it is going to be 1 in 10 to the power of 5. But for this called tunnel diode, it is 1 in 10 to the power of 3. 1 in 10 to the power of 3. So now what happens, sir? The device characteristics are completely changed. The new diode was announced in 1958 by a scientist called Leo Esaki. So this diode is called a tunnel diode. Why this is called as tunnel diode is the process of charge carrier transformation is happening something like a tunneling. And to remember his name, this diode is also called as Esaki diode. 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 Now we will discuss in detail why this tunneling is happening. Why this tunneling is happening. Okay. So we know that the barrier potential Vp is related with the width of the depletion region. So Vp is going to be Q Na by 2 epsilon into omega. Sir, this W, did you remember that W? What is W? W is going to be square root of 2 epsilon by Q into Na Nd by, or 1 by Na plus 1 by Nd into V naught. Did you remember this? The same thing is changed, sir. The same thing is changed. 2 epsilon by Q into 1 by Na plus 1 by Nd. This is what? Nothing but Vb. Simply is changed. That he has written W square. That's it. Nothing is changed here. Here Na is far greater than Nd assumed. So because of that, now what happens is you will get this. W square is going to be 2Vb by 2Vb epsilon by Qa. Don't think that. Yes, Mahendra, as the doping concentration is changing, the characteristics of the device also changes. Absolutely correct. You are absolutely correct. You got the point. You're bang on. So from the above equation, the width of the barrier varies inversely as the square root of the impurity concentration. So he's talking about W is inversely proportional to the square root of Na. So as this concentration increases, the width decreases. As the concentration increases, width decreases. That is what we discussed so far. So as the depletion width decreases, there is a large probability that an electron will penetrate. You understand this word penetrate. Penetrate is a word which you need to understand. What does it mean by penetration? Penetration is nothing but simply you are trying to make a hole. And entering it from this side. Trying to penetrate, not jumping. You are trying to penetrate. You are trying to create a hole and come out of that. Right? So now they are penetrating through the barrier. Mahendra, just listen. It is not a We are not calculating it, man. Hey, you are misunderstanding. See, for every, why we are calculating? We are not calculating, yeah. What we are doing, for every 10 to the power of 8 atoms, one atom is added. To make, for every 10 to the power of 8 atoms, one impurity is added for a normal PN junction diode. This is impurity I am talking. For every 10 to the power of 5 atoms, if this is one impurity is added, this impurity is added. Now what happened? This is called Zener diode. Zener diode. For every 10 to the power of 3 atoms, one impurity atom is added. This is called tunnel diode. We are not calculating it here. We are adding these are impurity concentrations. So as the doping increases, the width is decreasing. Did you get the point? Okay. So this will penetrate. So as the concentration you keep on increasing, they will not wait for the potential barrier to come down. What it will do is they will try to penetrate it through. They will try to penetrate. So that process is called. That process is called. That process is called tunneling. That process called. That phenomena is called tunneling. So this quantum mechanical behavior is referred to as the tunneling, and hence this high impurity density PN junction diodes are called tunnel diodes. And this is called, the phenomenon is called tunneling. Okay. So the energy band structure of heavily doped PN junction diode under open circuit conditions. So in the energy band structure for a lightly doped PN junction diode, the Fermi level EF lies inside the forbidden energy gap. Yes. So where it will be, sir? It generally this is going to be. So here you are going to have EFI, Fermi level. This is the Fermi level which lies between this is forbidden gap. In the heavily doped PN junction, EF lies outside the forbidden band. Either it should be here or it should be here. That is what it's talking about. So EF, we know that EF is going to be EC minus KT into ln of NC by ND. For lightly doped semiconductor, this ND is less than NC, so that ln of NC by ND is positive number. Hence, EF is less. If this is a positive number, this EF will be less than EC. So EF is less than EC. The Fermi level will be below the conduction band. So the Fermi level lies inside the forbidden band. So it means if this is the conduction band, it should be below the conduction band. So for heavily doped semiconductor, the donor concentrations are more. That is, ND is greater than NC. When ND is greater than NC, this term ln of NC by ND is negative. When this becomes negative, so now what happens, sir? So this also becomes positive. So and the Fermi level lies outside the forbidden band. Similarly, for EF is equal to EV plus KT into ln of NV by NA. So the forbidden gap. So for a heavily doped, so the Fermi level will be here. Generally, the Fermi level lies in between this EG. It will lie between this EG, forbidden gap. So, but here it is EF. You can see calculated here. This is going to be EC plus KT into ln of NC by ND is what we'll get. If it is the negative, what happens, sir? It will be in valency band. So if the heavily doped Na is less, greater than NV, the Fermi level lies in the valency band. This is what I am talking about. The energy band structure in a heavily doped PN diode under open circuited conditions, I will show. We'll show in the next slide. We'll show in the next slide. So Eg is going to be kT into ln of NCND by NCNB by N square, and E naught is going to be kT into ln of NDN by N square. This we know. Comparing above two equations for heavily doped PN junction diode, we find that E naught is greater than Eg. E naught is greater than Eg. Therefore, the constant difference of the potential energy E naught exceeds the forbidden energy gap voltage Vg Eg. So generally, this is Eg is nothing but we consider this as E naught generally. But here E naught is higher than Eg for a heavily doped. For a heavily doped, E naught is greater than Eg. E naught is greater than Eg. That is E naught is nothing but at equilibrium. At equilibrium stage, E naught is greater than Eg. Right? So the Fermi level EF in the P side is at the same energy level as the Fermi level in the N side. Note that there are no filled states on one side of the junction which are at the same energy as empty allowed states of the other, and there can be no flow of charge in either direction across the junction. See what is talking about this. This Eg, this is Eg. This E naught is very high. This E naught is very high when compared with Eg. E naught is very high when compared with Eg. So because of that, there is no charge flow, charge carriers flow. There is no charge carriers flow. So this is the empty state. This is the empty state, and this is the filled states for conduction band. So this E naught is higher when compared with Eg. E naught is higher when compared with Eg. E naught is higher when compared with Eg. Yes or no? You can see here very clearly. Now if you see the volt ampere characteristics, if the reverse bias voltage is applied to the tunnel diode, the height of the barrier is increased above the open circuit value of E naught. Already E naught is higher than Eg, and now again if you are increasing the reverse bias, E naught still increases. Hence the N side levels must shift downwards with respect to the P side levels as shown in the figure below. Is talking about this. So this is what happening. So when the reverse bias voltage is applied, this stage, now this EF is decreasing on N side. So this is applied reverse bias. Due to applied reverse bias, this E naught is changing. This is the barrier height. So barrier height is decreasing now. So now what happens, sir? There is a possibility to tunnel. There is a possibility to tunnel in this region. So we now observe that there are some energy states in the valency band of the P side which lie at the same level as allowed empty states in the conduction band of N side. If you go back and see what is the difference, here you can see here, is there any allowable states? No, there is no allowable state here. There are no allowable states here. So these both of them are the same energy level. So if you see here, you have some. Earlier it was here, but it is increased. When this is in valency band is increased. Now what's happening, sir? Here free states are existing. Here what is happening, sir? Here is what is happening, sir. You will have a possibility of tunneling. So this is what is happening. Hence these electrons will tunnel from the P side to N side, giving rise to reverse diode current. So as the magnitude of the reverse bias increases, causing the reverse current to increase. So consider if a forward bias is applied to the diode so that the potential barrier is decreased below E naught. Hence the N side levels must shift upwards with respect to those on the P side. The energy band diagram for a heavily doped under forward bias condition is shown below. You can see here. That is for either for reverse bias or forward bias. Just remember, tunneling process is happening. So slowly, as you increase the voltage now happening, sir. The tunneling happening. But this is first initially applied forward bias. This tunneling is happening. So again, you can see that more tunneling happening. Now slowly the tunneling decreases, and there is no tunneling at all. Four stages you should see here. Four stages you should see here. So either in positive forward bias or in the negative reverse bias, tunneling process will happen. Whenever you see there is a free region, then there will be definitely a tunneling process will happen. The figure A, we can observe that the electrons will tunnel from N to P material, giving rise to forward current. As the forward bias is increased further, the maximum number of electrons can leave from occupied states on the right side of the junction, and the tunnel. This is what I told you right just now. See, initially this tunneling is happening because there is a free space. These are the free spaces. So that electrons will try to tunnel. Now here. Now I will still increase further. Now what's happening, sir? This energy level is shifted. As the energy level is shifting, the tunneling process is again increasing. But at some point of time, this tunneling process start decreasing because this conduction band is decreasing. This valency band is decreasing. Right? As this valency band is decreasing, now what happens, sir? The tunneling process stops. Mahendra, I have explained you through this formula. This formula you see here, EF is going to Fermi level is going to be generally for a PN junction diode, EC is equal to minus KT into ln of NC by ND. So generally ND is less than NC. If ND is greater than NC, now what happens? ND is greater than NC. Now what happens, sir? This becomes minus. Ln of NC by ND becomes minus. So overall what happens, the Fermi level is above the conduction band. This becomes positive. Let's say this is 10 minus 2 earlier. It becomes 10 plus 2. So this is going to be minus 8. This is going to be plus 8 and this is going to be plus 12. Plus 8 and plus 12, Mahendra. So now what's happening, sir? So earlier it is supposed to be 8 here. It is, let's say this is 10 level. Now this becomes 12 now. So outside the forbidden gap. Pratyush Shukla, what do you mean by that? So are you asking about Schottky diode, pin diode? Are you asking about Schottky diode and pin diode? You have LED also. Yeah, you can read all of them. You can read LED and others also. Yeah, you should read it. You see, that's all just for 1 hour to 2 hour explanation. You can remember. Almost all of them will be same. Nothing wrong in Pratyush, nothing wrong in knowing all of them. If you have time, just go through all of them. Hope this is clear, Mr. Mahendra. Okay, right. We'll move on. These are the energy band diagrams. So tunneling increased to highest value, tunneling started decreasing, and tunneling stops. So these are the four for a positive half cycle, for a forward bias. For the reverse bias also tunneling happened. So now this is the beauty of this is the most important thing you should understand. Pratyush, obviously there is no more questions did not come earlier also. There may be a chance of not getting or getting. So we can't predict how the examiner will be. How the examiner will be. So many a times even tunnel diode question also not asked. We can't predict what examiner thinks. Okay. Now see the beauty here. This is the VI characteristics. This is the VI characteristics of tunnel diode. So very important, sir. Very important. Now see here. See here. For the forward voltage you are trying to increase. For the forward voltage you are trying to increase. Slowly the current increases initially and reaches to a point called V peak point. At this point, the current I becomes peak current and we call this current as a peak current IP. Peak current IP. Now, as you further increase the forward voltage, the current is decreasing. Sir, you understand here, generally V is equal to IR. V is equal to IR. As the V is increased, definitely I should increase anyway because IR is constant. R is constant. As the V is increasing, I should increase yes or no? I should increase yes or no? But here what's happening is inversely it's happening. Inversely it's happening. Inversely it's happening. It means the current is decreasing with the increasing the value of the voltage. With the increase of the value of the voltage. So now this region is called negative resistance region. Negative resistance region. Negative resistance region. As you further increase and increasing, it will reach to a point called valley point where this will become the lowest value. Peak point and valley point. So what do you mean by valley? Right? You see many valleys, right? You will see many valleys, right? So this is the peak point and this is the valley point. After this valley point, it again simply behaves like a normal PN junction diode. So how normal PN junction diode becomes, sir? The normal PN junction behaves like this. So this is what a normal PN junction behaves. So if you want to draw the normal PN junction diode behavior, if you don't draw the normal PN junction diode behavior, this will be this red line represents a normal PN junction diode behavior, right? So now, as the voltage is increasing, current is decreasing. Current is decreasing means who is increasing, sir? This R is increasing. This R is increasing means this is not resistance. This is actually resistance increasing means conductivity is decreasing. So because of that, this is called negative resistance region. Yeah, you asked a very good question, Pratyush, but it is not the right time to explain you that. It will take a lot of time for me to explain you about oscillations. How this negative resistance is used. Just remember here that this negative resistance region is used for oscillations. So when I am discussing about this concept, you can come and listen. So because that is not there in the subject, because along with you there are other students also listening to the class. I should also have the concern about the others. No, definitely I'll explain. No, you may not be having that concept in other things. Definitely I'll explain you in that concept of oscillations, right? So this is because I should also consider about other students also, right? Don't worry, don't worry. So now after this point of the voltage, valley voltage, the again the tunnel diode behaves as a normal PN junction diode. Normal PN junction diode. Normal PN junction diode. This is the VI characteristic of a tunnel diode. So he's talking about all this V peak point and V peak voltage. That all we have discussed. And this is valley voltage we have discussed. This is also the point which I mentioned very clearly. Valley current and valley voltage. And, if you further increase, now what happens, sir? It exhibits the same characteristics of a ordinary PN junction that I already explained. I don't want to spend much time on here. So this is a symbol. This is a symbol of a tunnel diode. Sir, as I told you, for a Zener, diode, what is there, sir? In the symbol of a Zener diode, there is a Z. There is Z in the symbol of P. So if you want to look like this, this is Z, yes or no? Z. For a Zener diode, you have a Z. Similarly, for a tunnel diode, you have a T. Simply just turn it around, make it 180, 90 degrees. And what happens, sir? You'll get like this. The symbol of a tunnel diode. The symbol of a tunnel diode. So this symbol of tunnel diode is equivalent to a series combination of RLC. Just remember, it is a series combination of RLC. Series combination of RLC. Actually, you will study this series combination of RLC in a subject called pulse and digital circuits. Pulse and digital circuits. And you can see here, you have something called a negative resistance minus Rn. Minus Rn. So as this is tunnel diode, you have a T here. 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 Okay. What are the applications of tunnel diode? It is used in very high speed switch since tunneling takes place at a high speed light. Okay. Now it is used as a high frequency oscillator. As Pratyush was mentioning, Pratyush, what you mentioned is here again covered. So I'm saying I am not trying to explain in detail, but remember that it can be used as a high frequency oscillator. High frequency oscillator. High frequency oscillator. And it can be used as a high speed switch. High speed switch. Now here comes another topic called photodiode. Photodiode. The photodiode is a device that operates in the reverse bias. The photodiode has a small transparent window that allows light to strike on surface of the PN, keeping the remaining sides unilluminated. Means, so all these areas are packed. All these sides are packed, sir. Only this side is open. If we try to only this side open and all other sides are packed. Only this side is open to make some light radiation. To make some light radiation. So when the light is falling on the junction, there is a current exists, and we know that it operates in reverse diode. Operates in reverse diode. So reverse voltage is produced. So photodiode. This is the symbol. The incoming light is incoming. Okay. The photodiode differs from the rectifier diode in that when PN junction is exposed to light, the reverse current increases with the light intensity. When there is no incident light, the reverse current I alpha, actually this is I alpha, is almost negligible and is called dark current. It is called dark current. An increase in the amount of light intensity expressed as irradiance produces an increase in the reverse current. So what is saying, sir? Very simple. So one side of you might have seen the laboratory, they will be like this. They'll come in the can. You'll have like this. Only the top is transparent. This top is transparent. So when you try to, this light is radiating, this current is existing, and you will get minus voltage. So some reverse current is flowing. So this is what photodiode. Photo is nothing but photons is existing. When light is incident on it, photons exist. That photons, because of photons, so this is converting a light energy into electrical energy. This is converting a light energy into electrical energy. It means, so this irradiance and a reverse current. If you increase the irradiance, the reverse current increases. Irradiance and reverse current. Irradiance and reverse current. Typically, the reverse current is approximately 1.4 microamperes at the reverse bias voltage of 10 volts with an irradiance of 0. This is what he's talking about. This is all the values which he's talking about, right? So therefore, the RR reverse radiance is going to be VR by I. So that's going to be 7.14 mega ohms. So at 20 milliwatts per centimeter square, the current is approximately 55 microamperes at. This is going to be VR, 10 volts. So now you can see here for different values of the voltages, different resistance is coming. So earlier the resistance is 7.14 mega ohms. Now we got 182 kilo ohms. 182 kilo ohms. So for the same voltage you applied, but power dissipation is changing. Now you got different resistances. Remember only one thing, that a photodiode can be used as a variable resistance device. Controlled by light intensity. Intensity. If you want to see, you can see here. So the reverse voltage versus reverse current. This is the VI characteristics. This is the voltage ampere, IV characteristics, or whatever VI characteristics, what you can call. So this is the dark current I lambda. Generally, we call this as what, sir? We call this as actually reverse saturation current. As I told you, photodiode must be operated only in reverse bias. The light is falling on it. Some current is generated. This is converting a light energy into electrical energy. Okay. So slowly the value is increasing. For 0 milliwatt. This is what light intensity is talking about. For different light intensity values, different currents are coming. So as you change the current light intensities, so what will get, sir? You change it different currents. You will have different currents. So what are the advantages of photodiodes? Photodiode can be used as a variable resistor device. Just now we discussed variable resistor device, and high sensitive to the light. Yes, it is very high sensitive to the light. The speed of operation is very high. Its operational speed is also very high, because it all depends on the value of light. Because light travels very fast, right? The speed of light is how much? 3 into 10 to the power of 10. So the speed of the operation is very high. So these are advantage. It can be used as a variable resistor. In a forward bias, photodiode acts as a normal p-n junction diode. So similarly, the Zener diode. If you use the Zener diode in forward bias, what happens, sir? It acts like Krishnaveni. If you use the p-n junction is a normal because it is irradiance. So if you use a Zener diode in a normal forward bias, what happens, sir? It acts as a normal p-n junction diode. Similarly, photodiode does not have any application in a forward bias. If you use in a forward bias, what happens? There is no use. That is the reason why we are not supposed to use a photodiode in forward bias. It is its property. The disadvantage is the dark current is temperature dependent. So as the temperature changes, this dark current values changes. I lambda value is changing. 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 What are the applications of a photodiode? Applications of photodiode. Photodiode are commonly used as alarm systems and counting systems. So did you see, observe this. What is alarm system, sir? Alarm system. Let's say there is a bank. There is a bank. Or let's say in your room. Let's say you have a secret room. This is a door. This is a door which you have. Right? So you stored some gold here. Gold or some money. Gold or some money. Gold or some money is here. You have some gold or money is, you put it this box, let's say, right? So when you lock it, what happens, sir? Completely this is, you don't find any light here. So completely this is dark. Completely this is dark, right? Let's say somebody is trying to open this door. When somebody is trying to open this door, let's say you have a photodiode here. A photodiode is connected to some alarm. Some speaker you connected it. Some speaker. Of course, in between you will have some inverter also. Don't worry. So when light is falling on it, current flows to this device and it will make some noise. It will make some noise. So it can be used in alarm systems or counting systems also. What do you mean by counting systems? Money counting, right? Money counting. Money counting. Money counter, you can use it. So continuously light is falling here now. When note comes, there is a break in the light falling on it. So how many times the light break comes, those many number of notes are fallen. Right? Those many number of notes are fallen. Those many notes, number of notes are fallen. So used in demodulators, this is not much important here. Encoders and decoders. This is called light decoder, light detectors. This is what I told you. That this is our light detector now. This is detecting light. This is detecting light. It can be used in light detection and used in optical communication systems also, because the photodiode is related to current. It is photodiode is related to light. So obviously it must be used in optical communications. Obviously it must be used in optical communications. Optical communications. Okay, this finishes today's topic. And here comes the bang on the Happy New Year 2021. I wish you all advance. See, why I did not open completely is still we are in the process of reaching New Year, right? Still we are in the process of reaching the New Year. We didn't yet reach New Year, but hoping that this New Year brings happiness to everyone. We had a very bad year. Actually, we had a very bad year to the entire humanity, 2020, and we are expecting a very positive results to come in the next year, 2021. Hope this 2021 brings very happy news for all of us. And of course, there is one good thing happened in 2020 is if 2020 hasn't come, I would have not started teaching on this Unacademy, and we did not make it is not possible for us to meet online like this. I'm happy that you're all we all met through this channel. I don't know whether we'll meet personally or not, but because of this process of online teaching, we met very easily, right? So this is the advantage. Hope you are enjoying my lectures. Are you enjoying my lectures or not? Are you enjoying my lectures or not? Are you enjoying my lectures or not? Please respond. No one there? No one is there? Yeah. Good, 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 Krishnaveni. Okay. So I wish you all a happy New Year in advance. Of course, tomorrow we are going to meet again. Tomorrow we are going to meet again. The tomorrow's class we will discuss about LED. We will discuss about LED and solar cell. In tomorrow's class, we'll discuss about LED and solar cell. Don't miss tomorrow's class. I have a surprise for all of you. We the channel of Unacademy Gate Telugu has a big surprise for all of you tomorrow. Big surprise for all of you tomorrow. Right? So we will move on. I wish you all a happy new year in advance. And this notes I am going to post it soon after the class in this Telegram channel. Telegram channel. This Telegram channel. Unacademy Gate Telugu. Okay. Explain scattering matrices. Do you want me to explain scattering mechanism or scattering matrices? Scattering mechanism. Sure, we'll take one day and I'll explain you. Need not worry, Krishnaveni will do that. And we have these are the YouTube channels of Unacademy. YouTube channels of Unacademy. So Creatix Gate EE, that is electrical engineering. ECE IN, this is for instrumentation. This is for instrumentation. And we have Unacademy Gate mechanical engineering, production engineering, and general engineering sciences. This is engineering sciences. And then you have Unacademy for civil engineers, Unacademy Gate for civil engineers, engineering Pathshala. We have very good channel list also. Unacademy computer science we have, especially for computer science and IT students. And we have Unacademy Gate questions. Complete only Gate questions will be available here on this channel. And we have Unacademy Gate Telugu channel. So we have a big surprise tomorrow. Big surprise. So just wait for the big surprise. Tomorrow we will have a big surprise. I'll let you know. Scattering mechanisms. Okay, we'll do that. We'll do that. Krishnaveni will do that. No problem. Right? And we have something called electrical junction. This is for electrical students. This is for electrical students. We have electrical junction also. This is for electrical students. This is electrical junction. These are the channels. And thank you. Don't forget to like, share, subscribe, and bell icon. Hit the bell icon. Hit the bell icon. Hit the bell icon. Thank you, and we'll meet again tomorrow. We'll meet again tomorrow. Bye for now. Good night. Good night. Good night, all of you.